Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
If P is an odd prime, I missed the word odd in the abstract, then P is congruent to 1 mod 4. That means P leaves a remainder 1 when divided by 4 if and only if P is a sum of 2 squares of integers. Yeah, so what does it mean? Let's take P equal to 5, the first odd prime, that is congruent to 1 mod 4, and then one can write P as 1 plus 4, and that's 1 square plus 2 square.
There you missed the word 2 while writing. You said it
Sum of 2 squares. You missed
Oh, P is a sum of 2 squares. Thanks. Okay, next prime, P equal to 9. Okay, no, it's not. So P equal to 13, which is 1 plus, let's write it like 4 times 3, which is same as 9 plus 4, which is same as 3 square plus 2 square. The next prime, which is of this type, is 17, is 1 plus 4 times 4. So when divided by 4, it leaves remainder 1. And then this is easy. This is 1 square plus 4 square. One can go further. One has to go up to 29. Here it is 1 plus 4 times 28, and that gives you, remainder 1. And this is 25 plus 4, and that's 5 square plus 2 square. So this is the theorem that we want to prove. There are other analogues of these theorems. Did I say it? Maybe I said it in the abstract, but these are all about the connecting a quadratic form to a congruence. So one is somehow saying that P is, so this relation, okay, so maybe I should define what a quadratic form is and then generalize this question and come back to this question. So yeah, no, but also I think this is saturated. So let us define what is a binary quadratic form. So binary means 2 variables. Quadratic means degree 2. And form means it's a homogeneous polynomial. So one could also talk about cubic, binary cubic forms, and Manjul Bhargava's work actually deals with cubic, binary cubic forms as well. Okay, so let's just go ahead and define Q is said to be a binary quadratic form if it can be written as, where ABCs are integers. So we are talking about quadratic forms or integers. So Z is integers. Okay, so why we generalize suddenly? We are saying that here there was a theorem of Fermat which said P is a sum of 2 squares. The quadratic form that there one is implicitly saying is x square plus y square. So this is an example of a quadratic form. And one is saying if P is a prime, can it be represented as a values of a quadratic form? So similarly one could ask the question. So here is another definition. We say that n, an integer, is representable or represented by Q if there exist integers x naught y naught in Z square such that q x naught y naught is an integer. So this is more general than asking for primes as sum of two squares. One is asking which integers are sum of two squares. This one can reduce. So in the case of squares, sum of two squares, because of the following identity. So what is the identity that we have? We can take this, we can take that, and we want to say that this is also sum of two squares. A lot of people would know this identity. This comes as follows. I can write this as x plus I y times x minus I y. If I should be more careful maybe, so I will write this as square root of minus 1 y, and then this multiplied by z plus square root minus 1 w times z minus square root minus 1 w. Now if I multiply these two, what I am going to get, so let's just write this down. I put them together, I get xz minus yw, and then there is a cross term, so let me put it like this, plus square root minus 1, and the cross term is going to be xw plus yz. And then this one, because of the negative sign, one can just see that the sign will appear here. So this will be the same fellow as here. And so we get that this is same as, I can substitute it here directly. I get this as xz minus yw xw plus y z square. So what it means is that if I am able to, if I have an integer, if I want to write it as a sum of two squares, perhaps I can factor n, and Neeraj may not agree with that. So let's assume that n is small, so we can easily factor, and then one can factor n into prime factors, and then each prime you represent as sum of two squares, and then you do this multiple times, and then you can write any integer n if you can write each prime to the power as sum of two squares. Now when there is a prime to the power, that power may be even. So it's now if so let me say it this way. If n is equal to say 3 square times 5 cube, then this is already a square, so this is good guy. We can take care of this easily. So we have to only take care of the non-square part of n. And there, if a prime p congruent to 3 mod 4 appears, we have a problem. We will not be able to do it. So I will not get into details, but these are the two things, these are the two aspects that I am trying to cover in this talk. One is, I have this quadratic form. If I multiply it by itself, I get the same quadratic form. So this is the composition. So I am taking a quadratic form, adding it to itself. If I decide to call this if there is such a thing as group, Q1 plus Q1 gives me Q1. So Q1 is an identity of some group, if there is a group that I am going to define later. And the other part is, I am defining, so this kind of composition will reduce the problem of writing an integer n or representing an integer n by a quadratic form to representing the prime factors of that n in terms of quadratic form. So this will reduce it to n equal to prime, and now for n equal to prime, quadratic reciprocity can be used to solve that problem in terms of taking it to congruences, that p congruent to 1 mod 4. That's a very easy thing to check, and it's actually computable. So if I'm given that p is congruent to 1 mod 4, I can use that to actually write p as a sum of two squares. So one can write a algorithm to do that. I'm trying to say this because Neeraj is around especially, and it's not such a bad algorithm. In fact, while I was preparing this, I am not sure if one can use, if there is a way of writing n as a sum of two squares will that help? Suppose I know that n is p times q, and suppose there is an algorithm independent of factoring n, of writing n as a sum of two squares. Will it be useful for factoring n? Is it possible to go other way? I didn't give it much thought, but just throwing it to you.
One thing for you is, in the definition, right, n is represented by q.
Yeah.
So you used q in two different places. One is that homogeneous polynomial quadratic form, and the other is the sum of squares. Use the.
Oh, okay, so this is an example. So I guess this is an example for Fermat. Because Fermat talks about p congruent to 1 mod 4 equivalent to
When in this
p reprintable.
definition,
Yeah.
what do you mean by q? In the definition, n in Z is represented by q.
Yeah.
If there exists the consistent q.
So it takes, there are some x naught y naught such that in this case, for example, in the case of Fermat, n equal to p, n is our prime p, and I am saying p is reprintable by q. The q suppose is in this case is this. Then I am saying p is a sum of two squares. That means there exists x naught y naught such that p equal to x naught square plus y naught square.
So you mean.
So the definition is for a given q.
Okay, so definition is for here general binary quadratic form. So I guess I didn't say it. Yeah.
For a given q.
Any given q, suppose q is a binary quadratic form, ABC integers, and then this is the definition. Maybe I should add a few more definitions right here. So you say that such a BQF, I'm going to say it BQF. So Q is like this, is primitive if GCD, greatest common divisor of ABC, is 1. The other definition is, one more definition let me put. We say that n is properly representable by q. So the q is the general one. If there exists x naught y naught such that, of course, q x naught y naught is n, and GCD of x naught y naught is again 1. Okay, so this is one more definition. All right, so let us move towards proving the first part, and then we'll go to the second part about in general compositions. So the aim is to prove Fermat's theorem, but actually to prove anything Fermat type. So aim is to prove Fermat type theorems, get a computational way of proving such theorems. Okay, so what I'm going to say now. Let's see. So here we have, okay, so one more definition. Discriminant of Q, discriminant of a quadratic form, binary quadratic form, delta is by definition, or delta Q is by definition p square minus 4ac. Okay. And then one of the things that follows, one can check this, that delta is always going to be either 0 modulo 4, so divisible by 4, or leaves the remainder 1 when divided by 4. This follows because when you take squares, b can be even. If it's even, square of even is divisible by 4. If it's odd, it's going to be 1 mod 4. And then it can be easily checked that if any delta which is an integer, so delta is an integer, which satisfies one of the two, E is a discriminant of some quadratic form. Okay, so one has this set of quadratic forms. Let's call this S not set of all binary quadratic forms over Z. Now this set, interestingly, so maybe one more thing I should define. So I want to say that its S naturally gets divided into S delta, delta congruent to 0 or 1 mod 4. So these are going to be the discriminants. S delta is by definition set of all binary quadratic forms of discriminant delta equal to delta q equal to, okay, that's it, fix that fixed delta, take all quadratic forms with that discriminant. Here is one more thing. We have written down, we wrote down q as this, but q is actually can be also thought of as an inner product, and here is how one can see it, and this is useful for proving some theorems. So we'll write it down. So this is really can be thought of as inner product. Of course, it comes in spatial relativity. If I take x square plus y square plus z square minus cw square, but in general, I think for integers now we are going to deal with this in two variables, and here was what we have. We can write it as xy transpose a b over 2 b over 2 c xy. So xy is this column vector, this is the transpose of it, this is the matrix that is associated to q. So q always will get associated to mq, and this is the matrix. So this I can write as, I am creating a notation here. I am going to suppose I denote this quadratic form in this notation as this, the corresponding matrix I will denote by mq, and I will use this for that. One consequence of this way of seeing it, writing it, is that delta of q then is turns out to be minus 4 determinant of mq. Yeah, this is a very nice thing. AC, this thing, 4 is there to adjust that, minus 4 is to adjust the sign. So this is same as b square minus 4ac. And now why is this good? I introduce a way of calling two quadratic forms equivalent. If there is a way of going from one quadratic form to another quadratic form by some linear transformation. Okay, and why is that linear transformation useful? Maybe I'll just do it by example. If I have this quadratic form, this is same as x square plus 2xy plus 2y square, and now let's calculate its discriminant. Let's call this q2. It's b square, which is 2 square minus 4, a is 1, c is 2, so this is going to be minus 4, and I guess I did not calculate this, but let me do it now. If I take q1 equal to the one that comes in Fermat, then you get that delta of q1 is minus 4, b square is 0, that's what you get. So discriminant of this and discriminant of this are same. In fact, it can be easily seen that there is a way of going from q1 to q2 by sending x to x plus y and y to y. Yeah, this corresponds to the matrix transformation 1 1 0 1 x y, and that is same as x plus y y. This is a matrix of integer with integer coefficients, and determinant is 1. This is actually the translation matrix. So in general, and so this has an inverse. So there is a way of also going back from q2 to q1 by substituting properly. I mean, I just don't want to write it. But what it means is that if q1, if there is a way of writing, so let us formally write this. What it means that q1, I take q1, I replace x by x plus y and y by y, that gives me q2 of xy, right? So if, and similarly I could write q1, I guess I have to do this now, q1 maybe is it, okay, so I'll just say it this way. So if there is an integer that can be represented as which way should it go? If q2 represents an integer, then I can take those x0 y0, and then now I will get q1 also represents that, because I will get the new my new x1 will be x0 plus y0, and my new y1 will be y0. Okay. So what I am saying is that if, so this is an easy observation. In this particular case, I am illustrating my example. So let me just say it again. If q2 represents n, then q1 also represents n. Okay, this can be easily checked because I can take, as I said, q2 x0 y0. This is equal to n is given, but then this is same as q1 of x0 plus y0 comma y0. This is reversible. This has an inverse, or also inverse lies in integers, and this can be formulated in a better way by using a group called spatial linear group with z coefficients. So SL to Z is the group of matrices P, Q, RS, let's say P, Q, RS all integers, and determinant is 1. So let me just say that P times S minus Q times R is 1. Determinant 1 implies the Cramer's rule will tell you that determinant comes down, and that's 1, so it's invertible in Z. So say this, one can have a proposition and a definition first perhaps. And again, all this is with the point of view of wanting to solve n, writing n as a value of a quadratic form, which n's are representable as sum of two squares or in general by a quadratic form. So we say that q1 definition this is actually in Gauss's terminology, this is proper equivalence, but we'll drop this word because, so he calls this proper because before that Legendre and Lagrange used something called proper and improper equivalence. Gauss realized that calling it proper, concentrating on only proper equivalences, is a better idea because it gives you a group. So you say that q1 and q2 are two quadratic forms, they're equivalent by SL to Z up to SL to Z. It's by definition if there exist PQRS sitting inside SL to Z. This is no big deal, just a notation. If this such that q1 of px plus qi comma rx plus sy equals q2 x comma y, right? And then there is a way of going back, because this is invertible, there is a way of going back. So this is gamma, if I call this a gamma, element gamma, so this is same as I have this q1, gamma is an element of SL to Z, acting on q1 gives me q2. Okay, so this is a group SL to Z acting on the set of quadratic forms, and that's my set S. So we have SL to Z, let's call this gamma, standard notation, gamma acts on. So whenever you have a group acting on a set, you can partition that set, and interestingly enough, it preserves all quadratic forms with a given discriminant. So that also is an easy consequence because of this way of writing that we wrote down here. So it can be easily checked just because of this, because determinant comes out and there is a transpose. So what will happen is that you will get m, so basically the relation will be something of the following kind: m of gamma times q, gamma acting on q will be same as gamma transpose mq gamma. Well, check this. If this is not good, then put the gamma here, other side. Okay, it is the right thing. So now if you apply determinant, you will see that determinant of gamma is 1, and so its square will come out. So that also tells you that earlier, for example, Legendre had said that q1 is equivalent to q2 if the determinant is plus minus 1. That would have been okay. It does work out, but Gauss said that let us concentrate only on SL to Z. These are small subtle points. It took 50 years, sometimes 100 years for people to realize, and you needed giants to realize that. So anyway, coming back, so we get that delta of gamma dot q is delta of q. So the discriminants are same, And so the discriminants are preserved. What it means is that gamma acts on S, but not only that, gamma acts individually on each S delta. Right. So now we can only concentrate on particular delta. Gamma acts on that delta. Let gamma act. Let it partition that S delta into its equivalence classes. So we get. So we'll say that. Okay, so maybe that's a consequence. Gamma in turn, gamma acts on each S delta. Hence, let's take S minus 4, which is said same as binary quadratic forms of discriminant minus 4. Remember that this includes x square plus y square. This is not a good way of writing it, but anyway. Okay, I mean, yeah. So this includes that, and I'm saying gamma acts on this. In general, gamma acts on S delta, and one is going to say now that one has this equivalence relation, so one can prove that this is an equivalence relation. That's obvious. If Q1 is equivalent to Q2, Q2 is equivalent to Q1, gamma inverse will come in and all that, and so we get a nice partition of S delta into equivalence classes. And where should I write it? So you get classes. So we have this definition. I'll just leave it this one here. So we have this definition that S delta, fixed delta, delta congruent to 0 or 1 mod 4, delta integer, take S delta. This becomes disjoint union of partitions. Maybe I should say equivalence classes of binary quadratic forms of discriminant delta. Yeah, and this is this thing theorem, which should I do it right now? Okay, I'll just quickly state the theorem. One of the main theorems. S delta. Okay, so this is running over. Let's say this is running over some equivalence classes. So I'm going to call this Q, and I'm going to take class of Q. So maybe this is running over some classes. Let's just say classes here. Q is in class, and then I'm taking all elements in that class. So I'm taking this set is really by definition all Q prime such that Q is equivalent to Q prime. Okay, and then when he's saying theorem 1 that number of classes is finite. Okay, so when he's saying take any delta, take delta equal to minus 4, there are only finitely many equivalent quadratic forms of discriminant minus 4. In fact, so this is one, maybe I'll just state it as part of this theorem. It's not of the same difficulty obviously, but I'll just say it. There exist okay, so I'll say it this way, every quadratic form, binary quadratic form of delta equal to minus 4 is equivalent to x square plus y square. Okay, so this is one very important consequence. This is also true for others, but it's not true for 20. So if I take delta equal to minus 20, I'll get the following kind of theorem. Oops, sorry. So this is quadratic form, let's say Q. I'm going to call it Q1, and Q2 is 2x square plus, I think it's 2xy plus 3y square. Let's calculate 4 minus 24 is correct. So these are the two, Q1 not equivalent to Q2. These are the only two for minus 20. Okay. Now if I want to turn this into a group, I'm going to, this is not what I'm following actually, but I'm going to turn this, if I want to turn this into a group, if these are the only two classes, I want to turn this finite set into a group. I want to somehow prove Q1 is identity. Q1 is going to Q1 times Q1 is Q1 because of something I will say. But let me tell you an identity about Q2. I want to somehow say that Q2 times Q2 is Q1. So Q2 is an element of order 2. And I wrote it down somewhere. Write it here. So what is Q2? Q2 is a quadratic form of discriminant minus 20 and the one that is given here. So 2x square plus 2xy plus 3y square. I am multiplying Q2 x comma y times Q2 y comma z comma w, and I am saying that this is same as Q1 something. So let's say what is Q1. Q1 is this, and the identity is two xz plus xw plus yz plus 3yw square plus 5xw minus yz square. So it shows that Q2 times Q1, somehow I want to realize that I'm jumping big time, but this is same as Q1. I want to somehow make sense out of this. This is one of the ways of making sense out of this. Qt is element of order 2, and class number of this is class number delta is 2. The class group has order 2. Okay, coming back to Fermat. By the way, it's an open question. It's an open question. If I take delta equal to delta equal to positive, it's an open question to show that S delta has only one class for infinitely many delta. It's a very big open question. So anyway, let's move on. So the real quadratic field should
For all positive delta,
take delta, run it over positive deltas, delta satisfying that condition. Then S delta has only one class. You want to show that there are infinitely many deltas, so that S delta has only one class. When class number of S delta, class number of delta, Q square root delta is 1 for lots of deltas. On the other hand, for delta negative, there are only 9 elements of class number 1. And that also was a big theorem. And it is always going to be finite at some big theorem as well. Okay, this equivalence gives you a very interesting theorem or proposition as follows. Let's say n is okay. I may have to put this later. If okay, let n be an integer representable by some quadratic form ax square plus bxy plus cy square, then there exists another quadratic form of the type okay, this is bad notation, not just say bqf by some quadratic form q, then there exists another quadratic form, binary quadratic form of the type nx square plus bxy plus cy square. Okay, so obviously if I take this, this is an if and only if, so printed then another quadratic which is equivalent to q. So what one is saying is that obviously if I take q to be this, I mean if I take q1 to be this, then q1, if I take q1 1 comma 0, that represents n. So but if q1 and if q1 is equivalent to q, then we know that q will also represent n. Right? What needs to be shown is that if n is representable by q, then there is some quadratic form which starts with n, meaning nx square plus bxy plus cy square, which is equivalent to q. That's the main thing. Okay, so let's just do that. Okay, what I want to say. So n is equal to ax square. Yeah, so okay, so this is how I go. I say suppose n is equal to q. Q is this given form, q p comma q. Then let rs integers be such that p times, what do I need? Let me see. So I am assuming that they are relative prime, so I guess I didn't say that. So let n be an integer properly representable, by some binary quadratic form q. Then, sorry, I think I'm not making good statements. Then there exists another binary quadratic form of the type this. Okay, that's okay. Suppose n is this, then let r comma s be in z such that p times r minus q times s equal to 1. Okay, this can be done because I am assuming properly representable. That means I am assuming that there is some p and q such that p and q are relatively prime. Okay, this is okay. This is okay because p and q are relatively prime by assumptions on being proper representable. Okay, and now there is some trick which I don't want to. It's basically you have to use the inverse of the corresponding PQRS. Let me just take a quick look. So I did not say it right. Let me just use this. PS minus QR equal to 1, and then it will turn out that Q of let's just do that, and then it will turn out that P of PX, Q of PX plus PX plus RY comma QX plus SY. If you write it, let's just write this guy. This fellow is, suppose this is ax square plus bxy plus big cy square, then this will become a px plus ry square plus b px plus ry times qx plus sy plus c y square, and the y is now qx plus sy square. And now if I expand this out, let's just look at the x square coefficient. You get a p square plus b p q plus c q x square plus I don't care xy plus again I don't care y square. Yeah, and now this guy is what we had. Suppose n is equal to pq, and then that is exactly right. This is qp comma q x square plus dot dot dot, and this is n. Okay, some trick, but it's a nice trick. It can be also proven that the things that you get here, when you actually put y equal to 0, x equal to 1, y equal to 0, are the are going to be relatively prime, but that's given. Okay, so I may be confusing you, and I may be confusing myself. Let's just move on. I mean, this is the fact of life. It turns out to be okay by this trick. And what is the main consequence? Let's just look at it. One is saying that if n is represented by a quadratic form, ax square plus bxy plus cy square, then there is a quadratic form which is equivalent to that quadratic form, which starts with n, meaning it is going to be n x square plus some b xy plus some c y square. Okay, this is very good because of the following lemma. And also, yeah, this is if and only if. This is obvious that it's an if and only if, because I can take 1 comma 0 as the value, and that will do that. Okay, guess I don't think I need this now. Okay, so let's concentrate then on. So if I want to so I say n is, okay, here is a definition. One more definition. N is representable by delta. Okay, this is a abuse of notation. N is representable by delta if there exists a primitive binary quadratic form of discriminant q delta q equal to delta such that n is properly represented by such a q. Okay. So let's just look at it again, why we are doing this. We have this quadratic form of discriminant minus 4, which is x square plus y square. We have said that it's unique, and now you want to check if n is represented by delta. We are going to say this because we are going to talk about represented by any element in the class, and we know that that class is finite. But if it turns out that class is number 1, then it will be anything which is represented by supposedly a big set is represented also by that one single element. Okay, that's the way we are going. So that's why this definition. And then we have this lemma. So take a quadratic form which is like this. Maybe I'll not call it a lemma, I'll just say, let's just look at the quadratic form like this. Let's calculate its delta. What is it? It's b square minus 4nc. Yeah. And so this is some fixed delta. Suppose I know, let me go it this way. Suppose delta is a square modulo 4n. Suppose this is given. So I know this much. Now I am going to create a theorem out of this. Suppose I know that delta is a square modulo 4n. Then I can write delta as x square plus 4n times some lambda. I am purposely choosing different, yeah. Then I can use this to say this, and then now if I put one more condition that n is odd. Why I do that? Do I need it? Okay, I don't do that. So if I put this condition, what does it mean? What I say is that suppose delta is a square modulo 4n, and that means what is given is that delta equal to, there is some bad notation, sorry, mu square plus 4n lambda, the delta equal to square plus a multiple of 4n. Well, this is equal to mu square minus 4n minus lambda. So now what I do is I consider q, I define it like this. I take it to be n x square plus mu xy minus, what is it I want? I want n is there, minus lambda y square. I guess this is what I want. What does it give? Okay, let's calculate its discriminant. It's going to be mu square minus plus 4n lambda. That's correct. Okay, so this is this means that suppose delta is a square modulo 4n, that means delta is this. Then if I take q to be this, then q, it turns out that q1 comma 0 is n. That means, this means, because of this definition, this means that n is representable by delta. Okay, this means there is a binary quadratic form which represents delta. Okay.
Which represents n. It's okay.
Yeah, n is representable by delta means, yeah, there is a q, as I said here, which represents n. Yeah, as you said, yes. Okay, so going to next lemma. Okay, I'll say it this way. Suppose n is a square modulo this thing, this happens, and this is an if and only if statement, and vice versa. I'll just say it like this. So that's the theorem. Okay, I don't want to. That's the main idea of the theorem. You just use that, and let's now turn it into a criteria. Let me prove as a corollary we get Fermat. Let's just prove that modulo the assumption that S delta S minus 4 has only one element. Okay, right. So this was proposition and proof together. So we have, now let's take P odd. So P is odd prime, delta equal to minus 4. I want to know if there exists Q such that delta of Q is the given delta and Q should represent P, the prime. Now, what is that criteria saying? It is saying that delta should be square modulo 4n. So I want that. Actually, there is a small problem here. I think I don't want a 4 there. So I have to do some trick and I have to get rid of this 4. Okay, so let me do it here itself. So if I assume that n is odd, it can be done. So I want to generalize this theorem a little bit. Okay, I'll just say it here. With more work, we can assume in the above that the congruence is modulo n. With more work, for n equal to odd, we can replace the condition modulo 4n by modulo n. Main point is that n is odd, 4 is relatively prime. This condition is a parity condition on the choosing of the right mu. That can be done independently of n because n is odd, and if something is divisible by 4 and something is divisible by n, because n is odd, you can assume that 4n also divides it. Okay, so that's the kind of minor thing that you have to do. You sometimes, one may not be able to take a nice mu. So if this mu doesn't work, you may have to take mu plus n. That will change the parity of mu by, because n is odd, it will change the parity of mu by, if it is even, it will become odd. If it's odd, it will become even. So that's the trick that you will need to do. So that's the more work that is needed. So I am going to use that. So I am going to say P is odd, P prime, delta is minus 4. Want to know if there exists Q such that delta Q equal to minus 4 and Q represents P. Now this is equivalent to, by the proposition that we proved there, that let's just copy it. Delta is a square mod. So delta equal to minus 4 is a square modulo P. Okay, so this is equivalent to minus 1, because 4 is already a square, minus 1 is a square modulo P. In the language of Gauss, or whatever, in the notation of Gauss, this is same as minus 1 quadratic residue of minus 1 modulo P is 1. That's what you want. The quadratic reciprocity is such that it turns this kind of equations other way around. So the P is below, it turns it around, makes it above. In this case, it's much simpler, and it becomes, this is same as the condition, minus 1 to the power P minus 1 over 2 equal to 1. But this is equivalent to, this is equal to 1 if and only if P is congruent to 1 mod 4. And so we get the theorem that P is the sum of two squares, two integers, sum of squares of two integers if P is a congruent to 1 mod 4. Similarly, so let's just move on. Now use this same delta, same trick, and we'll apply it to one more case. Maybe I'll write down the S deltas for that, and then you will believe me. There is also one reduction theorem that is going to go in, and I want to know how much time I have. Holy moly. Okay, so reduction theorem, how do I do this? Okay, so reduction theorem tells you, I'll just say it in words now. Reduction theorem tells you that take any quadratic form of a given discriminant, say ABC, you can cut down the size of B by using A. That's kind of clear, because you need to play with these few things and it will be clear. So let's just say it this way. If I take this matrix, what does it do? It takes x2, sends x to x plus y. In general, if I put an A here, it will send it to AY, it will send Y to Y. It doesn't change it. It's really a translation. Okay. If you apply it to the corresponding this guy, it takes B to B plus that, sorry, I should put an M here, clash of notation. This will take it to 2am xy plus whatever. So it changes, it translates this B by some multiple of 2a. So you can use the size of A to cut down the size of B. This is division algorithm. Okay. So you can use this to finally say the following theorem. The theorem says that if you take any quadratic form, you can, there exists a unique reduced quadratic form equivalent to it. And what does it mean by reduced? It means absolute value of B is less than equal to, so first A is always positive. We are talking about positively definite quadratic form, let's say now from here onwards, because reduction theory for indefinite quadratic forms is different and little bit complicated. So for positive definite quadratic forms, A is positive, delta is negative. We have absolute value of B. We say that something is reduced if absolute value of B is less than equal to A, less than equal to C. Okay. And then there is some trick about, when A equal to C, something happens, some extra thing. Let's just leave that. This is the condition. Now this condition, when you put with the condition that delta is fixed, it will force that there are only finite choices for A and B. It turns out that A is less than equal to square root of minus delta over 3 or something like that. Okay, but minus delta is actually positive, so it makes sense to say this. Once you say that there are only finitely many A, for finitely many A there are only finitely many B. For finitely many AB, because of the condition that delta equal to B square minus 4AC, there are only finitely many C. That forces that S delta, anything actually, but in this particular case the proof works for delta positive, S delta is a finite set. When you actually calculate it for delta equal to minus 4, you put those values, you calculate what the B's are, what the A's are, it will turn out that the only reduced one is x square plus y square. You can do it for 3, delta equal to minus 12, which is going to be 4 times 3. So 3 is the concentration, is really 4 somehow comes up, lags this. Always 2 is a problem, 2 is a prime which is a problem. So 4 always comes along. So anyway, so moving on. So you can for delta equal to minus 12 also you can calculate, it turns out to be 1. In that case, the quadratic form is x square plus 3y square. You can see that this is Q3, let's call it Q3 for, and then you can say that this is delta Q3, this is b square minus 4ac is minus 12. Again, this is one, this is a unique one. And then the question we are asking is p, there's one thing I missed here. Okay, so no one is lecturing, one always misses something. I would want that n to be relative time to delta. Okay, there is some problem with that. So I am going to take p, I am going to take not equal to 2 because there is a 12 here, and not equal to 3 because there is a 3 here in that 12. So when I avoid these two guys, the condition comes out to be p congruent to 1 mod 3 if and only if x square plus 3y square equal to p can be solved. Now I didn't check this, so let's just check it. So I hope it's correct. So let's take p equal to 3, 1 mod 3 means
This also p has to be a prime.
p is a prime, yeah.
Where did you use p prime in any of this?
Because we have to divide and conquer. Take an integer, composite, factor into primes. Solve for q equal to prime or prime power. But for prime power also we have same prime repeated again and again.
Now when you applied that lemma to this, right? Where did the primality come?
Okay, so that's a good point. It comes in, the reciprocity doesn't work very well when you have an n below. It's a good point, very good point. There's a problem, it's not an easy thing to calculate. It is doable, but it little unelegant. Not good for the lecture, let's say it this way. So
Somewhere in there is buried the fact that p has to be a prime.
it is easy to say, it is easy to calculate. Otherwise you can also factor n and then do it. So it can be done. It can be done. The general lemma, that is n for any n, that is it's indeed true. It's true for any n. Here I restricted it. Can be done, but needs some extra work because on the quadratic reciprocity front. Okay, so we can do this, and then where we are here. Let's just calculate for 1. If I take 7 is, I hope it's correct, 4 plus 3, it's correct. So 7, if I take 7, which is a prime, congruent to 1 mod 3, and then 7 is 2 square. 2 square plus 3 times 1 square. Okay, and so on. Amazing theorems. I mean, you can put phi and then you can calculate, but for phi, x square plus 5y square, remember there were two quadratic forms, x square plus 5y square, and then the other one is 2x square plus 2xy plus 3y square. And that's a problem. So you don't know which one represents it. And then for that, more work is needed, and that goes into deeper things. I want to say one last thing, and I have not talked about Manjul's work at all, but I'll just say, because we are now into quadratic reciprocity, and another open problem is very beautifully connected, and this particular thread will take us into modern number theory, and I want to say how it connects. Just one minute. So take elliptic curve E given by y square equal to x cube minus x. Take the modular form Fe summation a n q to the n equal to 1 to infinity. Fe is the modular form associated to E. You don't need whiles. It's true for CM ellipticus. Is modular form associated to E. What is Q? Q is e to the power 2 pi I tau. What is tau? Tau is a complex number. Imaginary part of tau is greater than 0. Said all that. What are these ANs? ANs come out by definition somehow calculating the number of points of the elliptic curves over Fp. And then using that you create a generating function. If you can drop this, you can just think of this as a generating function in variable q. Now the theorem is P is a sum of P's of the form n square plus 1, P is a prime. P is a prime, P is a square plus 1 if and only if AP, the pth coefficient appearing here is 2. This is also same, it's in the same line in some sense. When he's saying this question is open, by the way, the number of primes of the form n square plus 1, infinite conjecturally, not known. But here is something about the modular form, one single guy. This is a no control thing. This is one thing sitting in one single It's a single object. It's a single arithmetic object, telling you that if you calculate, if you are able to show that number of primes p such that AP equal to 2 is infinite, then this can be solved. So you know this is quadratic reciprocity. This is reciprocity taken to a different level. Okay, thank you.
There's one question. Sorry.
Yes, yes.
Somebody, I'm the one who understands at least, but asks all the questions, so I guess it must be too easy. This only works for positive definite quadratic.
No, negative also.
You made that somehow that delta has to be negative, right?
I made it only for this, but if you take, I mean, that's a big story as well. If you take it to be, you know, if you take the Pell's equation, so Pell's equation is x square minus 2i square, right? I mean, one of them. I mean, that's a one. What's the discriminant of this guy? Discriminant of delta q in this case is 8, right? So this is a real quadratic field, so to say, more harder. As you can see, you are solving for x square plus y square equal to n compact situation. X runs finite up to square root n, you run, y you run up to square root n, you are done. This guy is a negative and positive thing. Somehow you want to solve equal to 1. Suppose you want to solve this equal to 1. You don't know what to do. If you put a d here, it's bloody complicated. If there is an article by Lenstra in Bulletin, I think in 2000 something on this, one big article, the values of x and y for which d could be 17 or something, or d could be 29, and the size of x is huge. It's much more complicated to solve this. So computationally it's a harder thing, but reduction theory is there. Everything else is there. H delta is always positive, always finite. Number of classes is always finite. All these things work. Computationally harder. Any other question?
Main question. Are there primes which can be written as sum of squares in two different ways or multiple ways, and can one characterize?
I think not. Up to, you know, that usual thing, not.
So there is some.
There is a formula. I mean, yeah. I mean, the number of ways of representing n as a sum of two squares is summation. I mean, d dividing n, and then that formula can be calculated. I mean, there is the theta function comes in there. You can take qn square and summation, and then there is a formula. You can use this. You can prove Fermat by using theta functions, which is going again to Poisson summation formula and really good stuff also as well. But yeah, clear formula exists. But for n composite, no. And that's, I think, what I'm saying is that maybe, I don't know if this is.
Sorry, what is no?
I mean, if n is composite, and if I am able to write n as a sum of two squares in a faster way somehow, not square root n way, which is the usual brute force way, and then if I know that n is p times q, and assume that p and q are both good guys in the sense congruent to 1 mod 4, then can you use this to factor n, go other way around. I mean, that observation may be easier, but to write n as sum of two squares may be hard. Any other question? You had a question.
So just in the FE, an was the number of zeros on that elliptic curve modulo n.
Yeah, so this is, okay, so this is, yeah, so this is product over primes p not dividing, let's say p not dividing 4, 1 minus AP over 1 minus AP APT plus P T square inverse, put T equal to Q to the, what do I do? No, put T equal to P to the minus S. Okay, so APE is number of points of E over FP. Okay, you use a generating function, take the Euler product, put whenever the P to the P to the S appears, you will get an N there, put that, and then you get the thing. I am not saying it right, but I can tell you later. But basically there is a generating function. It's a bit involved. Yeah. It's like zeta function. You see, if I take zeta s, which is summation 1 over n to the s, I can, this is equal to product 1 minus, maybe this is a better way of saying it, right? I can do it like this. So you will get something like this. Then there is a naturally, what one associates to this is, I can associate q to the n to it, so to say. For every n, the coefficient of that n is 1. So if you have a n n to the s, I would put it as a n q to the n. So here on this side, I have something, some formula as a function of a n n to the s, n equal to 1 to infinity. And then use that n, you put it here and you get this formal thing, but it's actually not formal. You can put q as that value and still works out nicely as a modular form. But that's the way to go about defining it. Okay. Yeah, Manjul Bhargava weights. Amazing stuff.